Welcome to Get Your FRQ On. This question is from 2008. It's question 2, and it is calculator active. In the question stem, we have concert tickets going on sale beginning at noon and getting sold out at 9 p.m. We have a function L of t, which gives us the number of people in line waiting to get these tickets. We're given that the function L of t is twice differentiable, and we are provided with a table of select values of L of t at different values of t. In part A, we are asked to determine the rate at which the number of people is changing, the number of people in line is changing at 5:30, and to provide the units. So the rate of change of the number of people waiting in this line can be approximated by using a difference quotient over an interval that includes t equals 5.5. Now you'll notice if you look at the table, the link is provided below, that 5.5 is not one of the values of t in the table. So we want to make sure we use a difference quotient to approximate the rate of change using an interval that includes t equals 5.5. All right, I always like to use the smallest interval that contains it, so I'm going to approximate L prime of 5.5 to be L of 7 minus L of 4 over 7 minus 4, which using values from the table is 150 minus 126 all over 3, which turns out to be 8 people per hour. In part B, we are asked to find the average number of people waiting for the first 4 hours that these tickets are on sale using a trapezoidal sum over 3 subintervals. All right, so the average number of people waiting, this is an application of the formula for the average value of a function. So the average number of people waiting for the first 4 hours can be found using that formula, and we can set up an integral that would be 1/4 the integral from 0 to 4 of L of t dt. Now we are told specifically how to approximate this interval. We are to use the trapezoidal sum using 3 subintervals. So we would have 1/4 times, and then this is the really, really important part. You need to have an interval width times, in this case, an average of 2 function values. So the first interval has length 1, the second interval would have length 2, and the third interval would also have length 1, so that's why the 1, 2, and the 1 are there. But it's a trapezoidal sum, so we have to take the average of the 2 bases, 156 plus 120 over 2, 176 plus 156 over 2, 176 plus 126 over 2. This expression right here, the 1/4 times that massive expression, should be enough to earn you all the points for this part of the question, provided you have a label here. It is a calculator active question, so feel free to actually come up with an answer for this using your calculator. But it is 155.25 people on average over that first 4 hours. In part C, we are asked to determine the fewest possible number of times that L prime of t could equal 0 over the interval from 0 to 9. This is kind of a tricky question. The table that we have is for L of t, not L prime of t. So we can't just look at the table and say, well, it goes from positive to negative here and negative from positive here. We can't do that. We can't just count that from the table. But we can use the fact that L of t is twice differentiable. All right, so because L of t is twice differentiable, we know that L of t is continuous. But because it's twice differentiable, we also know that L prime of t is differentiable at least once, which implies that L prime of t is continuous. That's going to turn out to be important. Basically, what we're going to do here is we're going to use the intermediate value theorem, but one of the hypotheses for the intermediate value theorem is the function we're using it on, we must know is continuous. Well, we don't really know anything about L prime of t. We have L of t, we know it's twice differentiable, but we're expecting to use the intermediate value theorem on L prime of t when we don't know hardly anything about it. But what we can do is we can use this information about L of t being twice differentiable to conclude that L prime of t is continuous, which is a necessary condition for using the intermediate value theorem. So the way this is going to work is we're going to go through our table, And we're going to look at an average rate of change of L of t over an interval. So let's say L of 3 minus L of 1 over 2. That is positive. We don't need to know the exact value. We just need to know that it's positive. All right, and the way we use this is because that average rate of change is positive and L prime is continuous, right, and as well as L, we know that somewhere in the interval from 1 to 3, L prime of C is also positive. Right, so that is an application of our mean value theorem for derivatives. Because it's continuous, we know somewhere in the middle there's a value with that exact value as its derivative. Right? Now we can do the next interval. L of 4 minus L of 3 over 1 is negative. That implies that L prime of C is negative, somewhere between 3 and 4. Likewise, L7 minus L4 over 3 is positive, implying that L prime of C is positive, somewhere between 4 and 7. And L of 8 minus L of 7 over 1 is negative, which implies that L prime of C is negative for some value of C between 7 and 8. All right, so those four statements are all justified using the extreme value, or not the extreme value theorem, the mean value theorem, which we don't have to name. All right, we basically just have to do the work to show what's going on. But to conclude the fewest number of times that L prime of t could equal 0, now we're switching gears and using the intermediate value theorem. So notice we've determined that there's a C value somewhere in this interval where L prime of C is positive, then it's negative, then it's positive again, then it's negative again. We've already concluded that L prime of t is continuous, so if L prime of t somewhere goes from positive to negative to negative again, there are at least 3 sign changes in L prime of t, right? So if there's at least 3 sign changes in L prime of t, there has to be at least 3 times where L prime of t is equal to 0. All right, in part D, we are given if tickets were sold using the function r of t equals 550 times e to the negative t over 2, how many tickets were sold by 3 p.m.? All right, well, since tickets started to go on sale at noon, 3 p.m. is really t equals 3, and we can find this out using the fundamental theorem of calculus. So the number of tickets sold would just be the integral from 0 to 3 of r of t dt, or the integral from 0 to 3 of 550 e to the negative t over 2 dt. But this is a calculator question, so we're going to use our calculator to do this. Turns out it's about 972.784. So the number of tickets sold by 3 p.m. would be about 973 tickets.